Hey, welcome to another video of Chem with Com. This is a new topic called chemical equations and chemical reactions. These are the book chapters I cover in there. Um, yeah, first thing we're going to do is chemical equations and balancing. So let's take a look at chemical equations. We've been seeing some of these or glimpses of some of these, but we really haven't talked about them much. So here we go. We have stuff that we start with. Starting stuff. And we have products, stuff at the end. And all chemical equations are a list of starting stuff and a list of ending stuff, sort of, right? This is where the reaction takes place. And there's a little thing on the side. These starting stuff are called reactants. They're on the left side of the equation. Um, the products, the stuff at the end are products, sorry. And that's on the right side of the equation. The plus sign separates different individual reactants and products, right? So if you have two reactants, three or four or five, they're all separated by little pluses. The arrow means there's a reaction happening. And a reaction is just a rearrangement of atoms, basically. So rearrangement of atoms, usually. Sometimes electrons, but whatever. Rearrangement of atoms. Um, yeah. And there's something called coefficients. This just tells you how much of stuff there are. If there's no coefficient, it's a 1, right? So we have the reactants on the left. We rearrange those through some chemical reactions into some new products. Um, and we have the pluses separate them. The arrows tell you there was a reaction is. One thing I want to point out is we should have atoms should be the same on this side. Atoms on the reactant side should be the same as atoms on the right side every single time. We cannot lose atoms. We cannot gain atoms in the reaction. We just rearrange. Here we have 1, 2, 3, 4 red ones, 1, 2, 3, 4 red ones. 1, 2, 3, 4 white ones, 1, 2, 3, 4 white ones, one black one, one black one, right? So we cannot create or destroy atoms. We always have to have the same atoms on the reactant side, atoms on the product side, just like when you're cooking, right? If you start with, you know, pie mix, a couple bananas, and you make a couple banana pies, what if you had a couple apple pieces in there, right? Well, we can't have that, right? You didn't have apples in the beginning. You didn't have, so you can't have apples at the end, right? Just the same as, let's say you had strawberries here, strawberries on the reactant side. What if your pie ended up with no strawberries, right? We can't do that. That can't happen. They have to have the same amount start to finish. So cooking, I imagine this, like you have your ingredients, like let's say to make a pie, you put all of this in the oven, you finish it up, and you should have the same starting stuff as you ended with because you cannot create or destroy stuff, right? We're only rearranging things, and we're rearranging the bananas with the pie mix to make banana pies, right? So again, and this could have a coefficient of 2 bananas, just like this is 2 pies, all right? And 1 box of pie mix, right? So everything has its own coefficient. So if it's not listed, it means it's 1. All right. We're also going to start labeling states of matter. This is a chemical equation here with different states of matter. S means solid. Some examples are this sodium solid here. You have lead iodide, lead 2 iodide. You have water, that could be solid, right? These could be suspended solids in a liquid or dry solids in a container somewhere, right? Or on the bench top. L is liquid, lowercase l. Some examples are water, CH818, which should be octane. Gas, oh, sorry, liquid here, gas, H2, N2, O2. You could have gaseous water as well. Aqueous, we talked about this before. Aqueous, that shows up a lot actually, coming up in this chapter because we do a lot of chemical reactions in aqueous solutions. But yeah, you can have solids that are aqueous, and you can have these already ions that are aqueous. So aqueous means dissolved in water. Compounds like sodium chloride, when it says aqueous next to it, are actually already separated like Na1 plus and Cl1 minus into their ions because they're dissolved in that water solution. All right. Okay. So when we have a, if we look at cooking, right, we can have two different things on the ingredients list and a recipe, right? We have two different things. Usually when I Google something and it's like, hey, here's all the stuff you need. And then they tell you, exactly how much, and then they tell you how to assemble, right? An ingredients list is an unbalanced equation, meaning the starting stuff doesn't necessarily match up with the ending stuff, right? So when we start putting this recipe together, right, how much do we need of each? We start seeing these numbers, and it has to be the equal on both sides. Like the stuff it's made of has to be the same on both sides. So let's just take a look here. Without uh without a number in front, these are going to be one cheese, one bread, one sandwich. Let's check that out. All right. One bread, one cheese, one sandwich. Well, that's not correct because we only have one piece of bread here. Here we have two pieces of bread. So we cannot create bread from nothing. So this is specifically just an ingredients list because it's unbalanced, right? But look what happens when we start balancing these equations, right? We know we need two pieces of bread to make a sandwich. So we have one, two bread, one, two bread. We have one cheese, we have one cheese. So now it's balanced, right? Same on both sides. Before and after assembly of that sandwich. Now we can use these numbers in future things. I'm going to erase some of this annotation here. But we have ratios now. We have two pieces of bread to one sandwich. We have one piece of cheese to one sandwich. We also have two pieces of bread to one cheese, right? Those are the ratios from this balanced chemical equation or recipe, right? So again, unbalanced chemical equations are like an ingredients list. They tell you what's there, not how much of it. Balanced equations tell you exactly how much you need of each thing. So we look at molecules and chemical reactions, right? We know we could have a balanced equation, which all the amount of atoms link up and are balanced on both sides. But we could also have an unbalanced equation, which is just a list of ingredients. There's some amount of CH4. There's some amount of O2. There's some amount of CO2. There's some amount of H2. We don't know, right? We know there's at least one, right? If you go through a recipe, I can't remember the recipe website, but you go through a recipe website, they always tell you, okay, if you have potatoes, cauliflower, I don't know, chicken and stock, you can make some kind of meal, right? Soup or something. But so you know you need at least one of each, at least, because it's listed, right? But when the magic happens, when you get that right recipe and everything tastes perfect, you want to write down exactly how much you use, right? Or if the person tells you, the recipe tells you, you write exactly down how much they use. And here they use two O2 molecules with a CH4 to make one CO2 molecule and two H2O molecules. Again, it's just a rearrangement. Right, and let's count these again, right? We have four white circles. One, two, three, four. We have four red circles on the left and right. And we have one black circle, which is a carbon atom from left to right. So here it's balanced. And this is ultimately what we want. We always want to work with the balanced equations. There's no point in working with unbalanced equations. So one of the exercises here is we're going to balance these equations today. All right. So here, let's do some ratios, right? If there's no number, it's a 1. So if you look at the CH4, I'm going to erase some of these lines just to, oops, put more lines. Hold on here. Where are we? Erase some of these lines just so we could see it better, a little bit better. Okay. So we know these are 1. There's no number, they're 1. But let's look at the ratios. CH4 to H2O. That's a 1 CH4 to 2 H2O ratio. We also have this ratio here, 1 CH4 to 2 O2 molecules. We can do 2 O2 to 1 CO2. We have 1 CO2 to H2O. And you could build more ratios off of that too. Or is that all of them? Oh, yeah. You could do CO2 to CH4, O2 to H2O, right? So remember those. Those are going to be our mole ratios, and we're going to use those in our next chapter called stoichiometry, but we need those now. We're going to develop those. All right. Chemical reactions, just rearrangements of atoms, right? So let's say you go to build a sandwich at your house. Here at your house, you have many ingredients. You don't just have one piece of cheese and two pieces of bread, right? You have maybe a half loaf sitting there. You got those end pieces no one wants to eat. By the way, I make my daughter eat all those end pieces because as a baby, she was very resistant. Now she always gets the end pieces. We know we need cheese and we know it's going to make a sandwich, right? So we know we need at least one piece of bread, one piece of cheese, and it's going to make at least one sandwich because that's what we have, right? We were trying to make a sandwich. So we know if there's an ingredient or product, we must have at least one of those. Now, chemical reactions are just rearrangements of atoms. So whatever we start with, we have to end with. So since the product is a sandwich, we have to add this additional piece of bread because now it's balanced. Let's look at this. Bread, right? Cheese on both sides. Bread and cheese. All right. So here we have two pieces of bread. Here we have two pieces of bread. Here we have one cheese. Here we have one cheese. So now it's a balanced equation, right? So this is balanced. All right, let's try another one. Let's try something similar, right? In a chemical reaction, you have many reactants. You just don't have the exact amount, right? You have a couple beakers or glassware full of these chemicals or droppers, and you're adding them to each other. But there's not just one or five or six or 18 or even 100. There's billions upon billions upon billions in a chemical reaction, right? So that means what your chemical reaction is doing, it's just reacting with things that it wants to. And what it's doing, it's forming these products, right? Reactants being rearranged to products. So let's take a look. So we know that if there is a reactant or product, we have at least one of those. So that's our starting point. Our starting point is 1, 1, 1, and 1. Again, chemical reactions are just rearrangements of atoms. So whatever quantity of reactants we start with, we have to finish with. So since the products have 4 oxygen atoms, 4 hydrogen atoms, and 1 carbon atom, we need the same in the reactants, right? So then we added an O2 molecule and an H2O molecule. Now we have the same amount of atoms on the left and right sides of the equation, all right? Okay, so when we're looking at those, we can look at again, the ratios or the mole ratio, okay? So we look at CH4, there's one of them, and there's two waters. That's our mole ratio. That's like saying, and you could also say 1 dozen CH4s to 2 dozen. Oops. Yeah, so we can do this one, right? 1 dozen O2s. Let's just make this into O2 to make it easier. All right, so we'll just talk about the O2, but we could do any ratio we want, right? So we could do 1 CH4 to 2 H2Os. We could do 1 CH4 to 1 CO2. We could do 1 CH4 to 2 O2, which we have here, right? But that's a ratio. That means we could use a lot of different numbers with that. We could say 1 dozen CH4s to 2 dozen O2s, right? Because it's a 1 to 2 ratio. We could say 100 CH4s to 200 O2s. We can also say 1 mole of CH4 to 2 moles of oxygen. And that again is it's called the mole ratio. And let's give it a number, right? Because mole is a number of things. So it's just 1 times this many CH4s to 2 times this many CH4s, which is Avogadro's number, right? 6.022 times 10 to the 23rd. Could be anything, things, right? In this class, it's going to be atoms or molecules usually. All right. Balancing equations. This is hard. This is a mental block for a lot of people, so I'm trying to make it manageable for y'all. All right, so it's creating a recipe and using up all the ingredients. Okay, you've been invited to a potluck style party. You were tasked with bringing surf and turf burgers for everyone. 1 hamburger patty, 1 crispy fish patty, 3 buns, and a piece of cheese, right? All right, so you go to a burger shop and they don't have any, so you decide the closest thing is to buy a crispy fish sandwich and a cheeseburger and assemble them yourself. You don't want to waste anything, so you assemble all the ingredients you don't need into something else as well. All right, so we start with a cheeseburger and a crispy fish sandwich. This is the chemical formula for it, right? Cheese, hamburger patty, 2 buns. Cheese, crispy fish patty, 2 buns, right? All right, we take those are our reactants or our ingredients. We now rearrange them. We're in our car trying to assemble this before the party, right? So we assemble a surf and turf burger, which has crispy fish patty, sorry, cheese, crispy fish patty, hamburger, and 3 buns now. Kind of like a Big Mac, right? But we have a leftover bun and cheese. And no one's going to eat that at a party, right? We can't really serve a piece of bread and cheese, so you need to buy more ingredients to use everything up. So cool. I have to buy another cheeseburger and another crispy fish sandwich. So there's 2 of these, 2 of these. What I end up with is now 2 of the surf and turf burgers, right? So that's and when you look at the leftover stuff, now we can assemble 2 cheeses and 2 pieces of bun to make a grilled cheese sandwich. So this is the core of balancing. We're just putting these numbers on until the atoms or the reactant, the pieces of the reactants match the pieces in the products. Right? So they're even. And we're just going to add numbers until we're done. All right. This is how we're going to do this, how to balance chemical equations. The book, I think, has a way, but it's kind of like vague and convoluted. So I wrote this up. Take inventory of all the atoms or polyatomic ions in the reactants and products. So just figure out how much you're starting with, how much you're ending with, and then we have to change it from there. Select a reactant or product with the most atoms. Select within your selection. So let's say you pick something, and we're going to go through this. Choose an atom or polyatomic ion and balance them on both sides of the reaction arrow by increasing the coefficient on the reactant or product. Retake inventory of all the atoms in their reactants and products. Repeat steps 3 and 4 with the other atom that was in your original selection. Choose another atom or reactant or product to balance and repeat steps 3 and 4. Repeat step 6 as many times as necessary. Note, if polyatomic ions are together in the reactants and products, keep them together and do not separate those into atoms. So here you can see that NO3, which is nitrate, is the same in reactants and products. So keep those the same when you're doing your inventory. What happens is now right now there's one thing to balance, NO3. If you break that into two pieces, you have to balance the N and the O separately, and sometimes that gets very, very difficult, right? All right. This one actually might not be a great example for that, but yeah, let's continue. We'll look and see if it is, right? But this one for sure doesn't. NH4, ammonium dichromate, right? We have NH4 here. There's no NH4 here. So it's not the same on both sides of the reaction. All right. Okay, so don't do it for NH for this example. All right. All right, let's take a look here. I kind of broke it down into pieces. And this is the example we did very much earlier. Take inventory of all the atoms or polyatomic ions in their reactants or products. Here, we see there's one carbon, there are 4 hydrogens, and there are 2 oxygen atoms, right? Here, there's one carbon, 3 oxygens, because we have these 3, and then 2 hydrogens. So already we know we're not balanced, right? The hydrogens do not link up, right? That's not balanced, and the oxygens are not balanced, so we have to figure out how to do this. Select a reactant or product with the most atoms. CH4 has 5 atoms, so we're going to use that one. We're going to, with number 3 here, within your selection, choose an atom or polyatomic ion and balance them on both sides of the reaction arrow by increasing the coefficient on the reactant or product. So I chose 2. Now we have 4 hydrogens, but we also now have 2 oxygens here, 2 oxygens here. So now we have 4 oxygens total. So we have to redo inventory because we changed that coefficient. That's what we did there. We retook inventory and we had to increase the oxygen as well. So repeat steps 3 or 4 with the other atom. So the other atom was carbon. The carbon is already balanced, right? We have 1 on each side, so we don't have to do anything. All right, here. The last thing is now choose another atom or reactant to balance and repeat steps 3 and 4. So oxygen is the last thing. We need it to increase by 2 because we started with 2 and 4. So we need to increase it by 2. So we have to put a 2 in front. That gives us 2 extra oxygens, and now we are completely balanced. A lot of stuff in chemistry take time and practice to get better at it, but this one is especially you need a lot of practice, right? All right, so let's try this. Write a balanced equation for N2 and O2 to form dinitrogen pentoxide. First step, take inventory. Nitrogen, nitrogen, oxygen, and oxygen. Right? We have 2, 2, 2, and 5. All right. Next, we're going to choose with the most atoms. This one's not really super important because we only have 2 atoms, but when you have a long, complicated, equation like this or like this, you're going to have to be strategic with what you're doing. So we're going to choose N2O5, and let's balance the N2 first. Well, we're done. We didn't have to change anything. They're already balanced. Let's move on to oxygen now. All right, let's look at oxygen. I'm going to erase some of these lines just because they get a little distracting. All right, so now we have to balance the oxygens. I need more oxygens, right? And so what I'm going to do here is 2 and 5. 2 is the even number, 5 is the odd number, right? 2 and 5. The only number I know that they share is going to be 10. So if I put a 5 here, that's going to give us 10 oxygens, right? Now I need to put a 2 over here. That gives us now 2 times 5, that is 10 oxygens. So we're good on oxygens. But what that did is that also increased our nitrogen because now we have 4. So now our nitrogen is unbalanced. Well, let's look here. I have 2 and I have 4. How do I get 2 more nitrogens? It's starting at 1. There's 2 nitrogens. So what if I increase it to 2? Now that's going to give me 4 nitrogens. So I have 4 and 4 nitrogens, 10 and 10 oxygens. So this is the balanced equation. 2N2 gas plus 5O2 gas makes 2N2O5 solid. All right. So we basically did all these steps just kind of fluidly, right? So you can use this as a guide to help you with these equations. All right. Unbalanced equation. We're going to do inventory. I see a polyatomic ion here. I see a polyatomic ion here, but they're not the same on both sides, so we're going to leave them separate. Let's balance. Let's do inventory for the atoms. Okay. We have 2 nitrogens, 4 hydrogens, 3 oxygens. Here we have 2 nitrogens. We have 1, 2, 3 oxygens. And we only have 2 hydrogens. Again, I'm going to erase that to clean it up a bit. All right. Let's take a look here. Oops. Oops. There you go. Oh, where are we? All right. So find something with the most atoms. Well, to me, this one has the most atoms. And let's start with nitrogen. Done. Hydrogen. Oops. Nope. We need to fix that. So here it's lower. If we added, again, we're starting with a 1 here, but if we make that a 2, that now becomes 4 hydrogens. But now how many oxygens? We have 2 here, and now we have 2 here. So now that is 4. All right, let's just erase this to kind of get it back to where we are. So now we're good with the oxygens. Oh, sorry, we're good with the hydrogens. Now the last thing is oxygen. How do you balance the oxygen? Well, oops, I erased something that shouldn't have been erased, right? So now there should be a 2 here. Now we have 4. So we need to increase this one by at least 1. But this is already 1, so we have to cross that out and put a 2 now. So now that gives us, let's redo inventory. That gives us 6 oxygen, right? Which is more than we needed. Erase these check marks here. Now let's take a look. But let's balance it. We have to count everything else now. Now we have 4 nitrogen, and we have now 8 hydrogen. Now, how did we get all that now? Well, let's balance the nitrogens now. We have to have a 2 here because that gives us 4 nitrogens. Well, we still need to balance the hydrogens, so let's do that. We need 8 hydrogens, so we're going to put here a 4 because that now gives us 8 hydrogens. But that also gives us now 4, 5, 6 oxygens. Wait, looks like we're done. 486, 486. Let's rewrite it. NH 4, this is called ammonium nitrate, 2N2 gas plus O2 gas plus 4H2O liquid. All right. Balanced equation, right? The recipe tells us exactly how many we need of stuff, and we have no leftovers or no unused ingredients, right? All right, another one. This one now has the polyatomic ion in it, and it's before and after. So we're going to keep those together. And you'll see how much easier this is going to be with those polyatomic ions together. So we have hydrogen, hydrogen. We also have this calcium. Now let's do inventory. All right. PO4 we have, since there's 2 here and then 1 here, we have 3 total. Here we have 2 total. Hydrogens we have 3. Hydrogens here we have 2, but there's 2 of those molecules, so we have 4 total. Calcium we have 3. Here, calcium we have 1. All right, let's get to work. Pick the atom, okay, pick the molecule with the most atoms. That's going to be this one here. And again, this one isn't super important because there's only 3 things. So it didn't matter kind of which one you chose. It was all going to work out anyway. Let's start with the calcium. We have 3 on the left side, 1 on the right side. For us to even get remotely close to where we need to be, we need to put a 3 there because that gives us 3 calciums. But that also changes the, so it gives us 2 more. So we have now 12 hydrogens, right? Because we have, I'm going to write this out. This looks like this: H, H, P, O, 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 H, H, P, O, 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 O. That's what we're starting with. Let's say we did this by 3, right? Because that's what that 3 means. Now we have 12 hydrogens, right? And we have 2 phosphates, but we need to multiply that by 3. So then we have 6 phosphates. Okay, now calcium's balanced. We need to balance this stuff over here. Okay, so now we know we need to increase the phosphate by 3. So if we need 3 more phosphates, we have to put a 3 here. And that gives us now 6 phosphates because we have 3, actually, sorry, we need to put a 4 there, my bad. All right, because we're starting at 1, we need 3 more. So we need 4. So now that gives us 1, 2, 3, 4, 5, 6 phosphates. 6, 6, 3, and 3. We're almost there. But now that gives us 4 times 3 hydrogens. That gives us 12 hydrogens. So now we're all set. These are the same as this. Let's rewrite it. Calcium, so Ca3, PO4, double parentheses 2, and that's aqueous, plus 4H3PO4 aqueous makes 3 calcium H2PO4 with the 2 and then aqueous. So this is our balanced equation. All right, so go and give that some practice, and I will catch you next time.